topic we are going to discuss today is ligand substitution reactions. Transition metals undergo many types of reactions such as redox reactions, deprotonation reactions, and ligand substitution reaction. But we shall discuss only ligand exchange reaction. The reaction in which one ligand is substituted by another ligand is the ligand exchange or the ligand substitution reaction. The reaction takes place if the complex formed is more stable than the reacting complex. They involve either complete or partial exchange of ligands. We will restrict ourselves to the reaction of copper 2 complexes and copper 3 complexes. The ligands participating in the reaction will be water, ammonia, hydroxide and chloride ions. Copper 2 complexes. We add strong base like sodium hydroxide to the blue solution of copper sulfate. We observe a pale blue precipitate. So in this reaction, 2 hydroxides are replaced by 2 water ligands. So blue solution and the 2 water will be replaced by 2 hydroxyl to give pale blue precipitates. The hydroxide ion do not substitute water ligands directly. They act as a base and take protons from the water molecules, forming water and leaving hydroxide ions behind. The hydroxide ion thus made acts as a ligand in exchange with water molecules. Adding excess of ammonia solution dissolves pale blue precipitate, giving deep blue. So pale blue precipitates, and there is a substitution. And the 4 water molecules are substituted by the NH3, which is ammonia. So if we add aqueous ammonia instead of aqueous sodium hydroxide, we get the same observation. In this reaction, ammonia acts as a base and removes protons from water, leaving behind hydroxide ions. We substitute water as a ligand. This reaction is specifically called deprotonation reaction. So in these reactions, the protons are removed from the water and ammonia is acting as a base here. And when the protons are removed, the hydroxide ions will left behind. We substitute water as ligand. Blue solution, these are 6 water, and when 2 ammonia are interacted with them, so it will get deprotonated, and we got pale blue precipitates of the complex. So this is a ligand exchange reaction. Okay. Similarly, the water ligands in hexa-copper ion can also exchange for chloride ligands. This reaction gives yellow solution tetrachlorocuprate 2. Blue solution plus 4Cl gives us yellow solution plus 6H2O. Cobalt complexes. If we add strong base like sodium hydroxide to the pink aqueous solution of cobalt, we see blue precipitate of cobalt 2 hydroxide. Pink solution of cobalt plus 2 hydroxyl gave us blue precipitates plus water. Pink solution of cobalt is replaced by 6 ammonia ligands to give CuNH3 6 2 plus brown solution. Similarly, for the pink solution of cobalt, tetrachlorocobaltate, 2 complex is formed, which is of blue solution. Stability of complexes and stability constant, which is K stability. The equilibrium constant obtained from ligand exchange reaction in a solvent is called stability constant. The stability of complex is expressed in terms of equilibrium constant. The ligand exchange reactions are reversible, so we can derive equilibrium constant expression for such reactions. Deriving stability constant is similar to equilibrium constant. For example, we have this reaction, pink solution plus 4 chlorine, so it will give blue solution plus 6 water. So applying equilibrium constant expression, Kc is equal to COCl4 2 minus, and H2O will give in the numerator as because they are products, and the reactants will give in the denominator. Okay. Water is solvent, so it is in large excess, it is treated as constant and not shown. K stability is called the stability constant. The units of stability constant are calculated as those of equilibrium constant. The values of stability constant show how firmly a ligand is bonded to the central metal atom. Generally, the ligand atom will lower electronegativity bond firmly with the central metal. Those with high electronegativity values, this is why ammonia forms strong bond with metal ion and has higher stability constant. The data shows that complexes with polydentate ligands have higher stability constant value than those with monodentate ligands. So polydentates have high stability value. Now we have to discuss the redox reactions. Redox reactions are important here. The transition elements can exist in various oxidation states. In redox reaction, the oxidation state of transition elements are changed when they undergo chemical reaction under suitable condition. In redox reaction, transfers of electron takes place from one atom to another. The decrease in oxidation state is reduction, while increase in oxidation state is oxidation. Oxidizing agent is a species which accepts electron and undergoes reduction, and while the reducing agent that loses electrons and undergo oxidation. Reaction of acidified manganate 7 ions with the ethane diode ions. The reaction between ethane diode ions and acidified manganate ion is analyzed to find which way it will take place. The standard electrode potential of individual reactions are taken into consideration to check feasibility of overall reaction. Both reactions are taken in reduction mode. 2CO2 plus 2E gives us C2O4 2 negative, and MnO4 negative plus 8H positive plus 5E negative gives us MnO2 plus 4H2O. Now the question arises whether manganate oxidizes ethane diode to carbon dioxide or carbon dioxide oxidizes to manganese. The problem can be resolved by comparing the standard reduction potentials. The reaction with higher positive value is more likely to occur and proceed to right. The given reduction potential value indicates the manganate must reduce to manganese and should act oxidizing agent, while oxalate to carbon dioxide is a reducing agent. Okay. For writing the overall chemical reaction, the reaction with lower standard electrode potential must be reversed and taken in oxidation mode because it is oxidation reaction. So C2O4 2 negative gives us carbon dioxide plus 2 electrons. Electrode potential is minus 0.49 volt. Before combining the two half reactions, the number of electrons lost must equal the number of electrons gained. This can be done by multiplying the two half equations with different multipliers. So 2MnO4 plus 16H positive plus 10 electrons gives us 2MnO2 plus 8H2O. And 5C2O4 2 negative gives us 10 CO2 plus 10 electrons. So we can combine these two equations, and the final equation we got is 2MnO4 negative plus 5C2O4 2 negative plus 16H positive gives us 2MnO2 plus 10 CO2 plus 8 water with E is equal to plus 1.03 volt. Now we have the reaction of manganate with iron. So similarly we can calculate for the final equation for the reaction of manganate with iron. Reaction between copper and iodide. So copper can react with iodide to form white precipitate of copper iodide and red brown solution of iodine. And since we can split these two half equations. 1 by 2 I2 plus electron gives us I negative, and copper plus I negative gives us U plus. So the lower value of oxidation potential indicates that the reaction is inclined to proceed in the forward direction, making copper 1 a better reducing agent. However, this reaction proceeds in the forward direction because of the continuous precipitation of copper iodide in the reaction. So the final reaction, by combining these two half reactions, final reaction we got is 2 copper 2 plus 2 iodine gives us 2 Cu plus I2. Volume of copper sulfate solution is 0.03 decimeter cube, and volume of sodium thiosulfide in this example is 0.01 decimeter cube. And concentration of sodium thiosulfate solution is 0.05 mole per decimeter cube. Concentration is equal to mole per moles divided by volume. So moles we can calculate from this. So following two chemical reactions are involved in this. And when to calculate mole, we have to do the 10 divided by 1000 multiplied by 0.05, and we got 0.0005 mole of thiosulfate ions. And for the concentration of copper, we need to divide it with the 0.030 for the concentration of copper ions. So we got the final answer, which is 0.016 mole per decimeter cube. Now there is some stereoisomerism that is present in coordination compounds. First is geometric isomerism, and second is optical isomerism. So geometric isomerism exists, which is in the form of cis and trans isomers or the diastereomers. Like we have the complex diamine dichloroplatinum 2. So it can exist in the cis form and the trans form, as we can see in this figure. Similarly, we have octahedral complexes. They also show geometric isomerism. So we have already discussed that geometric isomers have different properties because of their different symmetry and polarity. The cis isomers are polar as they have imbalance of electron cloud and lack of symmetry. The end where water is ligand is partial negative, while the other end where ammonia is bonded gets partial positive. The reason is that oxygen of water has high electronegativity than nitrogen of ammonia, causing electron flow towards water. The two individual dipoles created by two water ligands result into net dipole, making the complex polar. Conversely, the trans isomers have symmetric shapes and even distribution of electron cloud, making them nonpolar. This is because the individual dipoles created by two water ligands work against each other, cancelling the overall dipole of the complex. Optical isomers. Optical isomers are molecules that have non-superimposable images. They are also called enantiomers. They have identical physical properties except for the ability to rotate the plane polarized light, either in clockwise or in the anti-clockwise direction. Optical isomers is exhibited by the octahedral compounds. And in case of octahedral, we have two monodentate ligands, two bidentate. Only the cis isomers can show optical isomers. So these are the mirror images. And three bidentate ligands, they can also show optical isomers. They are mirror images but are not superimposable on each other. So that's all for this chapter. Thanks for listening.